Good day everyone and welcome to your new computer science course brought to you by the Semester School. In this course, we will be covering the entire IGCSE and O-level computer science syllabus, so feel free to follow along in the playlist to cover your entire course over the next few videos. I will be instructor Saad Arfan. I have done my O and A levels in UAE and now I am a student in Fast Newses in Karachi. So let's just begin. First of all, we'll be covering chapter 1.1.1. To keep videos short, I'll be covering each sub-chapter in each video so you know exactly where to look and keep things very simple for you. We deal with data representation, and the very first thing we will talk about is binary. What is binary and why do we use it? So for that, let's move over to our board. You need to understand that computers are made of switches. Computers, I don't know if you've taken physics ever, but I'm sure you have seen something like this. It's called a diode and it's there in circuits, right? It lets current pass this way, but it stops current from passing this way. But we're not going to be studying physics right now, do not worry. But the point I'm trying to make is computers are made of circuits, and circuits in turn are made of diodes. Now these diodes are very simple, they're very primitive. They have only two states of existence. They either are on or they're off. They have a 1 or a 0. Now the computer is made of these. Therefore, it at the very basic level can only understand and deal with ones and zeros. Whether it's an image that we have, an image of some mountains, or a music video, anything we may have, it's ultimately converted and stored in these diodes, and the data is stored in ones and zeros. So ones and zeros make up numbers like this, 1011. This is a binary number. Bi means two, right? Binary, we call it binary because there's two possible states. We can either have a 1 or a 0. So that is the binary number system. Binary, as you can see over here, is the baseline for all of computing. Now, we have multiple number systems along with binary. We have the denary and the hexadecimal number system. So let's look at that in turn. Now, the denary number system, as you're aware, is just the number system we use in our day-to-day lives. 1, 2, 3, 4, 5, 6, 7, 8 till 9. In fact, there's a 0 here as well. You can see the possible number of digits are 10. We have 10 possible digits that represent our regular counting system. That's why we call it a base 10 number system. And that is called the denary number system. D-E-N-A-R-N-Y. So this is the denary number system. The binary number system, on the other hand, has only two possible digits to represent all of its data. Therefore, it's a base 2 number system. And I'm just going to write B here for the sake of your time, but you know we are talking about the binary number system. Finally, we also have another number system that goes from 0 to 9. It goes from 0 to 9, but it goes further beyond. And after 9, instead of 10, it comes A. And then instead of 11, we have B. And 13, C, D, E, and then finally F, which represents 15. But you can see in total, if we include the 0, we have 16 possible bits to represent data. Therefore, this is called a hexadecimal number system. We will look at the application and why we have hexadecimal soon enough. But for now, you can see that a number in denary is written something like this. We have 23, we have 102, and so on and so forth. In binary, we have numbers that are just basically sequences of ones and zeros. This binary number could represent anything. It could represent a word in a text file. It could represent a note in a song. It can represent anything. And then we have hex, which we will cover shortly. For now, you just need to know that it is a base 16 number system. So let's go back. Now that you know about the number systems, we need to look at how to be able to convert them. When you look at this binary number, when you look at this binary number, you don't really understand, do you? You understand 23, it's a number, it's a simple number, it can represent 23 oranges, 23 anything, and there's 23 of them, you're aware of that. But binary, how do we understand binary? We don't. So usually for human understanding, we convert binary to denary, which is our number system. How do we go about doing that? That's what we shall cover right now. So let's say we have the number 20. In fact, it's easier if we start with converting binary to denary. So let's say we have 1011. This is a binary number. Let's look at how to convert it to denary. Now in binary, in fact, I'm going to write it out here separately because we need to explain a certain concept. That is that in binary, we label each bit with an index 0, 1, 2, 3. Now 0 here is the least significant bit, and as you move forward we get to more and more significant bits. Each digit here, we call it digit when it's in denary, like for example 20, we have 2 digits, but in binary we call them bits. So each bit has an index. Just like over here we have units, tens, and then if we had another number here it would be hundreds, thousands, and so on. So you can see units is the least significant. In maths we have studied significant and significance of bits, right? Where the rightmost is the least significant bit, and then as we move left it gets more and more significant. So just like there's most significant digits, in binary we have most significant bits and least significant bits. There's a terminology. This is the LSB, least significant bit. This is the MSB, which is the most significant bit. So now, to convert this binary number to a denary number, we look at the indexes and we take them and we put them to the power of 2. So this binary number or binary bit 1 is 2 to the power of 3. This would be 2 to the power of 2, but since there's a 0 here, we ignore it. We don't write anything here. We're converting from binary to denary right now, by the way. Then here we come down and it's 2 to the power of 1. And here it's 2 to the power of 0. Now we know any number to the power of 0 is 1, and 2 to the power of 1 is 2. We ignore this, and then 2 to the power of 3 is 8. This would be 4. If this was a 1, we would take it and it would be a 4. So now again you can see how the binary number has 2's everywhere. It's binary, it's 2. So each bit represents 2 to the power of its index value. And then to convert it to denary, we add up those index values. So we have 8 plus 2 plus 1, which gives us 11. Thus, we can say 11 in denary base 10 is equal to 1011 in binary. This is the conversion from denary to binary. So now we know how to convert any binary number to a denary number. Let me give you an exercise. Let's say we have this number 1111. I want you to pause the video and try converting it to a denary number using these set of steps that I showed you. Okay, I imagine you have paused the video and you are resuming it now, so let me show you the set of steps again. As always, we take each number, each bit in this, and we give it its index 0, 1, 2, and 3. Then we only consider the bits that have a 1. In this case, all of them have a 1. So we will be adding all their values. In this case, in this binary number, we did not have a 1 here in the index 2. So we did not add 2 to the power of 2 to it. So in this case, we take 2 to the power of 3 plus 2 squared plus 2 to the power of 1 is just 2 simply, and 2 to the power of 0 is 1. So adding these up, we get 2 to the power of 3 is 8 plus 2 squared is 4. So 8 plus 4 is 12. And then 13, 14, and 15. So the answer is 15. This is our answer. Now that we know how to convert from binary to denary, let's look at something that's a little more tricky, but not by much. That is to convert denary, to convert denary to binary. Let me erase this real quick. Now there is a simple method to do this as well, and that is to first of all make a table like this. Table with rows and columns. So we put our number 20 in the top left corner here, and then we divide by 2. What do we get? 10. What was the remainder? The remainder was 0. Let's divide 10 by 2 again. We get 5. What is our remainder? 0. Now, converting 5 by 2 will give us a decimal number normally, but we don't want it in decimal. We want the quotient and the remainder. So 5 divided by 2 gives us the quotient of 2 and a remainder of 1. And finally, 2 divided by 2 gives us 1 with a remainder of 0. Now, do you notice something? This sequence is of 1s and 0s, right? We take this and that gives us our binary number. So starting from here, being our most significant bit, we get 1, 0, 1, 0, 0. Now, again, from the steps we saw here to convert our binary to denary number, we can test our theory out. Indexing it, we get this is 0, 1, 2, so we take 2 square plus 3, 4, so 2 to the power of 4. Now what is 2 square plus 2 to the power of 4? 2 square is simply 4, and 2 to the power of 4 is 16. So 4 plus 16, what do we get? We get 20. So now you know how to convert any denary number to a binary number as well. Simply write it out in the top left corner of a table you make, right? And then this is unnecessary. We can just erase this part. Don't get confused. This is part of something else. Yeah, so we have this table right here. I'm outlining it. Right in the top left, we successively divide by 2 until we get a 1, and then we write out the remainders as well. Then we start from here, from the bottom, work our way up, and that gives us our binary number, our equivalent binary number. Therefore, we can say 20 in base 10 is equivalent to 10100 in base 2 in binary. Thank you very much for watching this video and joining me on this lesson. In the upcoming videos, we will be continuing the data representation topic of computer science and covering extra topics such as the hexadecimal number system in more detail, as well as topics such as the addition of binary numbers. I hope you learned something from this video, you enjoyed the video, and I hope to see you in the future videos as well. Take care.